So last time we discussed stimulated Raman scattering. Or sometimes known as SRS for short. And we derived sort of the effective nonlinear susceptibility for the Raman scattering process, right? We basically saw that that there is an effective third order nonlinear susceptibility chi3, right, which sort of describes the coupling of the pump and the Stokes waves through the optical phonons, right? And so we derive the nonlinear susceptibility and also the nonlinear polarization that is induced due to this process, right? So once we have the nonlinear polarization and susceptibility, we can just like for any other nonlinear process, we can try to get coupled amplitude equations for the propagating waves and see how they get modified as they propagate along the medium, right? Starting from the canonical propagation equation. So let's do that. So to remind you, the canonical propagation equation of nonlinear optics, right? So let's say I'm writing this for the Stokes wave, so I have a subscript S for Stokes. Right, so this is a familiar canonical propagation equation. We've seen this many times, right? So last class we derived this nonlinear polarization, right, which is, for example, induced at the Stokes frequency due to the Raman coupling. So we can just substitute that nonlinear polarization that we derived, right? So again, we can write this as the chi3 due to Raman. Right, and then the three fields were AP, AP conjugate, and AS, right? So omega P minus omega P and omega S gives you omega S, right? And then this e to the ikz comes because we write E is equal to A times e to the ikz. So this goes along with this, and this we get, so this A times A conjugate, so the e to the ik factors cancel out. Right, and this 6 is the degeneracy factor because all three terms are different. Right, and we saw last time that this Raman susceptibility had both real parts, right? So it had a real part which we'll see modifies the refractive index. So it will be something like the intensity dependent refractive index that we had seen earlier for the electronic chi3. And it had an imaginary part which will lead to gain or loss. Okay, so we'll see it leads to gain for the Stokes and loss for the anti-Stokes. Okay, so if we plug this expression into the propagation equation and explicitly write the real and imaginary parts separately, then So we get these two terms, right? So the first term has an I out in front, which means this is just a phase, right? So this factor just modifies the phase of the Stokes as it propagates. And so this is like an effective refractive index, right? And which is proportional to mod AP square. So it's proportional to the pump intensity or pump power, right? So in other words, this is something like cross phase modulation due to the pump, right? Except that the nonlinear susceptibility here is the Raman susceptibility. Okay, so the usual cross phase modulation has just the chi3, which is the electronic chi3, right? But here there's an additional phase shift, which is due to just the Raman nonlinearity. Okay, and then this term here, you can see it doesn't have an I, right? So it's just a real quantity, which means so you have dA over dz equal to some constant times as, right? So depending if that constant is positive or negative, you will either get exponential gain or decay, right? So this is like a gain or loss depending on the sign of this, right? So if, for example, the imaginary part of chi3 Raman is negative, then the negative with this negative become positive, so that will be like a gain, right? And if this imaginary part is positive, then this will be like a loss. Okay. So and last class we had already derived expressions for this chi3 Raman, right, at the Stokes and anti-Stokes. And you can see that the gain, again, the gain or the loss would again be proportional to the pump power. Okay. So we can try sort of write this in terms of the pump intensity. Okay, right. So we know that the intensity is related to the field amplitude like that, right? So we just replace AP square by the intensity. So you can rewrite these equations with just the constants modified here. So okay. So we introduce these constants N2R, okay, which is basically the nonlinear index coefficient due to Raman. Okay. So again, when we were initially looking at chi3 and self-phase modulation, etc., we saw that there was an intensity-dependent refractive index, right? Which was so the bare refractive index N0 plus there was an additional refractive index N2 times I. Similarly, right here also the refractive index gets modified by some constant times the pump intensity. That constant again we can call it as some N2, but this time due to Raman. Okay. So yeah, so this is the nonlinear index coefficient due to Raman, and then the other term since it's a gain or loss, we call it G sub R, so the Raman gain coefficient. Okay. So we can write what these constants are. Basically. Right, so this N2R is basically proportional to the real part of the Raman nonlinearity, right? So at omega s, for example, again, right, due to omega p minus omega p omega s. Right, so this is the nonlinear index coefficient due to Raman. Right, just like we had a nonlinear index coefficient due to the electronic chi3, there also N2 was some constant times chi3, or in that case, sort of in the climbing symmetry limit, chi3 was real. And then this GR, you can write it like this. So this is now proportional to the imaginary part. Right, and this is called the Raman gain coefficient. Okay, so basically, if you go back and look at the expression for this Raman susceptibility, so for the Stokes, this imaginary part is negative, right? So this gain coefficient is positive, which means you get amplification, right? The Stokes wave grows as it propagates. Whereas for anti-Stokes, this is positive. Okay, so there, of course, we need to replace S by A, right? Omega A, omega A, omega A here, right? So imaginary part, the Raman at omega A is negative, is positive. Right, because they were opposite signs, you remember? So that means for that, this will be negative. So we can call a loss coefficient, which is the negative of the gain coefficient, and that will be greater than 0. So for the anti-Stokes, the propagation equation will be right? So just like the Stokes, you'll have one part which modifies the refractive index, right? And then the second part, instead of gain, you'll have a loss. Okay, so you can see that in simulated Raman scattering, basically the Stokes wave will grow, and if you send in any anti-Stokes, that will should actually get attenuated, right? So at the output, you should only see significant power in Stokes, but at the anti-Stokes, you should not see anything. But it was found initially in many experiments that they were actually seeing quite a bit of the anti-Stokes. Okay, so initially it was sort of mysterious as to why we are seeing anti-Stokes also, because the anti-Stokes should actually get attenuated, right? So the reason for that, can anybody try to guess how you can generate an anti-Stokes? Think of maybe some other nonlinear process which could also be occurring in the medium. So one clue is that, remember that the Stokes and anti-Stokes frequencies are symmetrically placed. So right, the Stokes frequency is about Raman shift down from the pump. Anti-Stokes is Raman shift up from the pump, right? So does this arrangement of frequencies remind you of something? Where have you seen this arrangement of frequencies, like a strong pump in the middle and then
So four-way mixing.
Four-way mixing, right? So in four-way mixing, we saw that like a strong pump could lead to gain for these signal and ideal frequencies which are detuned symmetrically from the pump, right? So in the Raman case, also we have Stokes and anti-Stokes frequencies here, which are of course getting modified due to the Raman nonlinearity, but they can also couple through the four-way mixing nonlinearity, right? And like you can see that there would be a term which goes like the four-way mixing, right? So here we've taken terms as which go as mod AP square times AS or AA, right? But okay, so right, so the reason why sometimes anti-Stokes is seen is that you can imagine if these now also couple due to four-way mixing, then the anti-Stokes and Stokes will experience gain due to this strong pump, right? Due to the four-way mixing nonlinearity. So how does that happen, right? So again, we took terms here. So for example, we were looking at term which went as omega A. So we took omega p minus omega p and omega A, right? Similarly for the Stokes. But there could also be terms like, for example, if I want to
Sir,
look at, yeah.
sir, which factor will determine that four-way mixing will be stronger or surface modulation or Raman will be stronger? Raman effect will
Yeah.
be stronger.
So yeah, we'll see. We'll see. So what you can sort of guess already, right? So what was an important consideration in four-way mixing, right? For four-way mixing to be efficient, we needed to satisfy some condition. What was that? Do you remember? Right. So energy conservation. If these two are detuned, then four-way mixing was this process. Remember? So if these two are equally detuned, then energy conservation is satisfied. But then on top of that, we also had to satisfy momentum conservation or phase matching, right? And if the process was phase matched in the medium, right, then we saw that these could get amplified by a large amount exponentially. But if they were phase mismatched, then this process won't occur efficiently, right? So this whether this term is significant compared to this Raman terms would be again if you have phase matching in your medium or not. Right? So if we want to look at the nonlinear polarization, let's say at the anti-Stokes frequency, right? So these terms we got by writing something which went as mod AP square AA, right? So omega p minus omega p plus omega A. But could there be other terms, right, which also go as omega A, right? So now we have, let's say, the Stokes also present. So from here, you can see that omega A is 2 omega p minus omega s, right? Which means there would be a nonlinear polarization term which varies with the frequency omega A, which goes as AP square AS conjugate, right? Omega p minus omega s, right? And this looks like a four-way mixing term. Remember, I mean, if you remember our discussion of four-way mixing, we had terms like square of the pump, and then so the idler went as the signal conjugate, and then the signal went as the idler conjugate. So similarly, there will be a Stokes polarization which goes as AP square AA conjugate, right? Right. So this this four-way mixing like interaction between the Stokes and anti-Stokes, there is a specific term for it. It is known as CARS or coherent anti-Stokes Raman scattering. Okay. So whenever an anti-Stokes with appreciable power is observed, that means your medium is supporting CARS, right? If just sort of normal Raman scattering is happening without this four-way mixing like interaction, then you will only see Stokes and not anti-Stokes. Okay, so we can see what this term looks like. So recall our last class where we wrote down the nonlinear polarization due to this coupling of the field with the phonon in the medium or the lattice vibration, right? So that polarization went as the product of this, the amplitude of the vibration Q, right? Times the field, the optical field which has, let's say, the pump and the Stokes. Right, this capital K was Kp minus Ks, and this capital omega was omega p minus omega s. So now, if you want to look again for a term which goes as e to the I omega a t, right? Then omega a is this omega p plus this capital omega, right? So you can see that would go as the product of this AP and Q, right? So if we look for term which goes as e to the I omega a t, right? So then that coefficient we can write like this. Right? Because so the AP product of AP and Q will give me something which goes as e to the I this capital omega plus omega p, which is omega a. Right? So this omega a is omega p plus omega. Right, and then also in the last class we had derived an expression for this Q of omega, right, which depended on the pump and Stokes amplitude, if you remember, right? So the Q here went as APAS conjugate, right? So then you can see that this term, if this goes as APAS conjugate, then this term will go as AP square AS conjugate, right? It's basically this. So explicitly, you want to write, so Q of omega so you look at the notes from your last class, so Q of omega was right. So the vibration at the frequency capital omega is excited by the product of the pump amplitude and the Stokes amplitude, because the pump amplitude goes as omega p, and then AS conjugate is minus omega s. So omega p minus omega s is this capital omega. Right? So the beating between the pump and the Stokes gives you excites the phonon. Right, and then there is this factor in the denominator, depending on the detuning. So if you put this expression for Q here, you can see that you'll get PA, which is proportional to AP square AS. Right? Yeah, and then we also need to take into account the spatial dependence. So that goes as e to the I Kp plus K. But capital K is Kp minus Ks. right? So then this factor goes as two Kp minus Ks. Right, so again you can see we are getting something like a four-way mixing, right? So now when we put this P of omega A into my canonical propagation equation, right? So then on the right hand side I get the polarization times e to the minus ikz. So for the anti-Stokes I need to multiply by the e to the I minus ikaz. So you can see you'll get a factor 2 Kp minus Ks minus Ka, which is like the wave vector mismatch for the four-way mixing, right? Right, so we just write it explicitly. Right, so for the stars, so P, so the nonlinear polarization at omega A, right, goes like that. So this is something like the four-way mixing interaction. So again, we can define this as some effective chi3, right? So we can call this as 3 epsilon naught chi3 the sub f for four-way mixing, but sort of now due to the Raman coupling. Right, the factor 3 here is because now two of these frequencies are the same, omega p, omega p, omega s. So there are three permutations. Right, so now again, if we write the canonical propagation for anti-Stokes here, right? So you have some constants here, then you have the nonlinear polarization at omega A, and then e to the minus I kaz, right? So you can see that this term will go as something with AP square AX conjugate with I e to the I delta k z, right? Where delta k is now 2 Kp minus Ks minus Ka, just like we had for the four-way mixing due to the electronic nonlinearities. Right, so now if this delta k is 0 or close to 0, right, then you see that the anti-Stokes will get amplified due to this four-way mixing interaction. So if this can overcome the loss due to the sort of the simple Raman interaction, right, then you can see an appreciable anti-Stokes. Okay, so it depends on whether you can satisfy this phase matching condition in your medium or not, right? So again, depending on these frequencies and the dispersion in your medium, if this phase matching criterion is satisfied, then the anti-Stokes can also grow. If not, then you will only see the Stokes and not the anti-Stokes. So I hope that's clear. So again, there are various applications for these cards, like in biological imaging and microscopy, etc. Okay, so now, so we go back to this Stokes propagation equation, right? So it had a sort of a phase, a nonlinear phase here, which you can cite it. Right, and then this gain term. So now we can see how the intensity in the Stokes wave goes, right? So we can find out what dis by dz is. So again, is is 2 epsilon naught c times mod as square, right? And this as is mod as square is as times as conjugate, right? So we can write this as okay, and then for these das by dz and das conjugate by dz, we can use this equation and its conjugate. So if you go ahead and do that, you see that you just end up with one term. It goes like that. So the intensity of the Stokes wave on propagation, you can see that it's sort of just growing with something proportional to the Planck intensity, right? So this GR is the again the Raman gain factor, right? So this GR, if you go back again, we have written the expression for this. So it is proportional to omega s, right, or proportional to 1 over lambda s, and some other material constants in the medium, like right, the atomic density, the mass of the atom or molecule, and this d alpha by dq, how the polarizability changes with displacement, etc. Right, so materials which have a large GR will give you a large Raman coupling, right? So we can look at some representative values. So for silica, glass, right? Right. For example, optical fibers. This value is about 10 to the minus 2 centimeter per gigawatt. Right. So units of G are meter per watt, because so you have dis by dz here, so which means the coefficient of is here is per meter, and we know that I is watt per meter square, so this is meter per watt. So it's usually represented in centimeter per gigawatt to have sort of reasonable units here. Okay, so this is GR. So silica is about 10 to the minus 2 at a wavelength of about 1 micron. Right, and silica is an amorphous material, so we saw that how the Raman susceptibility sort of gets broadened over a very wide region, right? And so automatically the peak sort of goes down. That's why this value is quite low. If you go to crystalline materials, right, for example, silicon, then this Raman gain is much larger, so it's 20 centimeter per gigawatt, so like 3 orders of magnitude higher at 1.5 micron. Right. And then diamond carbon lattice, carbon with a diamond lattice, It's also crystalline, same structure as silicon, right? With this carbon instead of silicon. Also has people have even seen larger, like up to 50 centimeter per gigawatt. Around 1 micron. Okay, so basically, in general, crystalline materials will have larger GR values than silica, right? So by this GR, we are meaning the peak value, right? So remember that the Raman susceptibility and hence the Raman gain has alignment, right? So it depends on actually the detuning from your peak gain, right? So this GR is the peak. So crystalline materials have narrow resonances and high values of GR, whereas amorphous have sort of broadened resonances with lower values. Okay, so you can see straightforward here that the Stokes gets amplified, right, at a rate proportional to the pump power. So we can make amplifiers out of it, right? And Raman amplifiers are now quite commonly used in almost all fields of optics and photonics, right? And they're especially important in optical communications because you want to send optical signals over a long distance and they get attenuated while propagating the fiber, right? So you need to periodically boost them using amplifiers. So Raman amplifiers are basically amplifiers built out of the Raman interaction where you have a strong pump wave and then the signal that you want to amplify is the Stokes. So depending on the wavelength of your signal that you want to amplify, you want to send in a pump which is a Raman shift higher than the Stokes, right? So you can see that, I mean, the solution to this equation is very simple, right? So after a length L in the medium gets amplified by factor which is exponential in the pump power, right? So in terms of the power, so I can write the output power by input power as e to the g, and then the intensity I write as power divided by the mode area, this A effective times that, right? So this is basically the gain of the Raman amplifier, right? So you can see it goes exponentially with the pump power length and 1 over A effective, right? So so that's why, for example, with optical fibers, even though GR is very low, right, but you can make very long lengths with fibers, right? And A effective is also fairly small, right? Like few micron square. So you can get pretty large amplification factors with optical fibers.
Sir, here
then,
we have
yeah.
Sir, here we have assumed the pump power to be constant. The intensity of
Yes.
the
So
pump.
this is in the undepleted pump
Regime.
regime, right? So so typically, yeah. So let's say you want to amplify by a factor of 100. If you send in a pump power which is sort of 1,000 times your input signal, then even after amplification, the pump sort of is undepleted to a very good approximation, right? So in that case, this is fine. So if you look at some numbers here, so right, so initial all these amplifiers and even now a lot of the amplifiers you get in the market are built out of optical fibers, where you can just have long lengths, right? But recently people have started going to these crystalline materials and making on-chip waveguides, right? So then you can sort of shrink these Raman amplifiers to a very small size, right? So now your Raman gain coefficient is very large. You can go to very small lengths. And with these on-chip waveguides, you can also make A effective very small, much smaller even than the optical fibers. So you can sort of reduce L and also this pump power and go to small compact devices with these crystalline materials. So if you take some numbers, right? So for a standard optical fiber, the GR value is that, and then the optical mode area is about 50 micron square. So if you have a length of 1 kilometer of fiber, okay, so this factor is GRPL over A. Can be roughly like about 2 or 3. So this G value can be about 10 for a pump power of about 1 watt. Okay, to give you some idea of some numbers. Okay, so this was actually a big breakthrough in optical communications because so you know that EDFAs, erbium doped fiber amplifiers, are sort of the standard amplifiers which were used in optical communications, which works on sort of the standard population inversion and stimulated emission. But they have a very limited range. So they work for wavelengths between like 1530 to 1560 nanometer, right? And so it was fine for a long time, but then as data rates have been increasing and the internet is sort of exploding, you need more and more wavelength channels in your optical communication network, right? So now people have started using wavelengths over a much bigger range, right? From let's say 1500 to 1600. So then how do you amplify these other wavelengths, right? And then so Raman amplifiers came to the rescue. And now you have like very complicated kinds of designs where you have 3-4 different pump lasers at different wavelengths. So each of their gain spectrums sort of add up to give you some very nice flat gain over a very broad bandwidth. Okay, so that's one application for SRS, is Raman amplifiers. And you know that the next obvious step, if you can make good amplifiers, then the next obvious step is, okay, can I place this amplifying medium inside an optical cavity and make a laser out of it, right? So the same thing you can do with Raman also. Right, so this simplified model didn't take into account, as you said, pump depletion. Also, it didn't take into account propagation loss, right, while propagating the fiber. So, for example, the pump will get attenuated as it's propagating. Similarly, the stokes will also get attenuated as you propagate. So, right. So, for example, in the Stokes equation, you need to add another term which takes this propagation loss into account, right? Which will offset your gain a little bit for practical amplifiers. But if your propagation lengths are small enough, right? So this alpha in optical fibers is about 0.2 dB per kilometer. So you can see for 1 kilometer this loss is very small, 0.2 dB is nothing. Right? But if you start going to, let's say, 10 kilometers, that's 2 dB. Right? 20 kilometers, so 15 kilometers is 3 dB, that's a factor of half. Then you need to take into account. Okay, so just like with other types of lasers or OPOs that we discussed, right? We have this Raman SRS which can give us gain, right, for the Stokes. So we can again place, if we do this interaction inside an optical cavity, right, then if the Raman gain exceeds the loss in the optical cavity, then if we pump hard enough using just a pump wave, right, then due to the Raman interaction here, so any noise at the Stokes gets amplified, and if the gain overcomes the loss, then you get lasing at the Stokes. Right, without sending any input Stokes, like, so we just send in a pump, and then once the pump exceeds the threshold, then you get Stokes out. Right, so if I plot the Stokes power out versus the pump power in, then basically until you reach the threshold, you get nothing. Then as soon as you exceed the threshold, right, you start getting red light up. Just like any laser. Right, so now again, if you're doing this in a cavity, so recall that our optical cavity had resonances, right? And if you wanted to do this efficiently, then okay, so we pump at, let's say, one of the cavity resonances. So let's say this is frequency. So I pump at one of the cavity resonances, right? So that the field builds up inside the cavity. And now you get Stokes scattering a Raman shift away, right? So now, again, just like for the OPO, we wanted to line up the signal and idler frequencies to cavity resonances. Here also, this scattered, so the Stokes frequency here better line up with one of the cavity resonances for this process to be efficient and for you to get a reasonably low threshold, right? If it doesn't line up with the cavity resonances, then basically the Stokes doesn't build up at all and it leaks away. So then how do you again ensure this? You can try to sort of have your cavity FSR here as sort of a sub-multiple of the Raman shift, but that's practically sort of almost impossible to do because especially for these micron scale on-chip cavities, because any tiny variations will shift your FSR here and easily you can be miselect. So
Can you explain the frequency diagram again?
So we are pumping at one of the cavity resonances, right?
Okay.
And then the Stokes scattered light is one Raman shift lower in frequency than the pump, right?
Yes, sir.
So the Stokes frequency will be omega p minus this omega r, right? But this lasing will happen only if the Stokes is also at one of the cavity resonances, so that it sort of makes multiple round trips in the cavity and acquires the gain, right? But let's say when this is lining up with the cavity resonance, the Stokes lies somewhere here, so it's in the, it doesn't line up with any cavity resonance. That can easily happen, right?
Yes.
because this depends on like your some cavity size of the cavity and dispersion properties of the medium, etc. Right? So this could very easily, or most probably, it will land somewhere not at a cavity, right?
Okay.
So in that case, this lasing won't happen, right? So for that, what you need is this, like one of the cavity resonances to uh, line up exactly with the Stokes, right? In that case, now your both pump and Stokes are at cavity resonance, and you have what is called a doubly resonant condition, right? Where both pump and Stokes circulate in the cavity, and Stokes acquires gain, and you get it. But so, how to ensure this, right? One way is, of course, if you can, I mean, you can think of that if FSR is a submultiple of this omega r, right? Then you go like some integer multiple of the FSR, then you will again arrive at a cavity resonance. But we had earlier seen that FSR is sort of not constant; it depends on the dispersion properties, right? And it's also very sensitive to sort of the size, the circumference of my cavity, etc. So this is practically very difficult to do, right? So basically what people do is, so you remember here that there's actually a bit to the Raman gain, right? So so this peak is at omega r, downshifted from the pump, but there's a line width, right? There's a Raman line width here. Again, which is sort of the inverse of the phonon lifetime in the medium, right? So now, if we make the cavity big enough, right? So this FSR, if you recall, was inversely proportional to the length of the cavity. Okay. So if I make the length large enough such that the FSR now is small, okay, and specifically if you can make the FSR smaller than this Raman line width, right? Then basically what will happen is that for sure you will have at least one resonance within your Raman line, right? I hope that's obvious, right? So if you ensure this, then basically you're for sure to have a Stokes mode which lines up with the cavity. So this is sort of the, so you choose some length such that this condition is satisfied. So explicitly, this omega FSR, if you recall, was 2 pi times C over NGL, where NG was the group index, L was the length of the cavity. Right, so this is 2 gamma because the whole full width is 2 gamma. Right, so this means that if your L is bigger than this value, then you can ensure this doubly resonant operation and basically an efficient laser, Raman laser. So this gamma is a material property, Ng is also material property, like the dispersion in your medium. Again, we can do a simple analysis to find out how this threshold power that we need scales with properties of the medium and the cavity, right? So recall, like go back again to our OPO case. We saw that so this optical cavities can be described by something called a Q factor, which is basically the resonant frequency divided by the line width, right? And we saw that in the OPO, the Kerr OPO case, that the threshold scales with 1 over Q square. Right? So we can see for Raman lasing, sort of what are the metrics involved. Right, so we can do a simple analysis. So we can write the propagation equation again for the Stokes. So the Stokes power so if you look at the Stokes power inside the cavity, okay, so we can take some loss. Right, so let's say this is like again a ring cavity or something, and the field is propagating like that. So as it's propagating, some of it can be scattered due to roughness or be lost due to scattering. So we take some loss, propagation loss. And then if it's coupled with the pump here, with the Raman interaction, then it has the Raman gain, right? So so this Raman gain factor goes as the pump. So basically the task is if you can balance this loss with this gain, then you can get lasing for the Stokes. So basically threshold happens when this loss is equal to gain. Right? Okay, so now this pump intensity is inside the cavity. So I put a subscript C. Right? And basically what we are interested in is what power we send in through some coupling waveguide from the outside, right? So there is a coupled intensity or power here, C, and then which is related to the input power here again through this factor of the finesse that we talked about. So the intensity again is the pump power inside the cavity divided by this again mode area.
But the video has gone off.
That right? So now this pump power within the cavity, again recall that the pump power in the cavity was related to the pump power we send in from outside by this factor of the finesse, right? So this F is the finesse of the cavity with sub P means at the pump frequency. Right. So again, this was assuming that the pump is exactly on the cavity resonance, right in the middle of the cavity resonance. The power in the cavity gets enhanced by a factor of finesse. Right, and then recall this finesse was related to the Q factor by this mode number. Right, and the mode number was basically how many wavelengths fit in my cavity, right? So the cavity length divided by lambda over n, which is the lambda in the medium. That's my m. So this is some integer, right? Some large integer. So from here, basically, the finesse I can write as q times lambda divided by L times n effective. from there, if I put this expression for the finesse into here, the power inside the cavity, the pump power inside the cavity, I can write as this factor, which is proportional to Q times the input power. Okay, so that means so now if I look at the pump intensity, which is P divided by the mode area, right? So that I'll have a factor of the mode area here, and I already have a factor of the L. So again, mode area times L, right? So mode area is the cross-sectional area. So if I look at the cross-section here, and then L is the length, so that's the mode volume, right? A effective times L will be the mode volume. So the intensity inside the cavity I can write like that. This is the cavity mode volume. Right, so the intensity inside the cavity is Q over V times my input pump power. So I want a high Q and low V. Right, small cavity, which is high quality factor, which means it has low loss. Right, so that sort of with that we can put this on the right hand side, right? But now on the left hand side we have alpha, but that alpha also determines Q, right? So alpha is basically the rate at which the power is getting lost as the field propagates in the cavity, right? And basically the loss is what gives the cavity the line width, right? So Q, which is the resonance frequency over the line width, is basically related to this loss, right? The lower the loss, the higher the Q. Right, so the power is being lost in the cavity like e to the minus alpha z, right? As right, and now again we can relate z to sort of a time scale by using z is the velocity times time, right? So we can write this as, we use this same trick previously when we were discussing OPOs also, right? So I write z as c over n effective times t, so the speed of light times time. Right, so now I have an expression for how the field inside the cavity decays with time, right? But we know that that's the definition of the Q factor, right? Basically, the field decays with time and how many oscillations of the field there are before the field decays, right? So e to the minus omega s over Q, right? This is basically the rate of loss of the field, right? That's the definition of the Q factor, if you recall. So, in other words, so this is e to the minus p over some tau cavity, right? Where the cavity lifetime is Q over omega. Right? So you can directly see basically the cavity lifetime is, so Q is the number of cycles 1 over omega s gives you sort of the time period. So the number of time periods before which the field decays. Okay? That's given by Q. Okay, so basically these two quantities are equal, right? These are just two different ways of writing the same thing. Either you write in terms of the Q factor or you write in terms of the propagation loss. So then basically we can relate Q to alpha from here, right? So from here basically omega s over Qs. So this is at S means the Stokes at the Stokes frequency. Passive and effective, which means alpha is omega s over C write in terms of wavelength like this lambda and effective over Qs. Okay, so basically for alpha I can substitute this factor, which also now depends on Qs. Okay. So for the intensity we can substitute that, and for alpha we can substitute this. Okay, so if you do that, right, so on the left hand side I have 2 pi over lambda s Qs. Right hand side I have gr times that. So at this gain equal to loss condition, I say my input power is the threshold power. Right, so from this I can get the expression for the threshold power, this power here, after which I get lazy. Right, so from there you can see this threshold power. Okay, so threshold power scales with mode volume, right? So a smaller cavity is better. That would mean a lower threshold power. It scales inversely with this Raman gain coefficient, right? So if you have a material with a large Raman susceptibility or the Raman gain is large, then again the threshold power is low. And then inversely scales with the product of the quality factors with the Stokes and pump resonances, right? And so if they are not very different, then again this is Q square, right? So again you want a good quality optical resonator with a very low loss for a low threshold. Again, so initially a lot of the work was done with fibers, right? So you sort of wrap around a fiber and make a cavity. And of course, for that, the V effective will be large because the fiber length will be large, right? And the quality factors are also not great because sort of when you couple out and in back into the fiber, either you have to come out of into free space and then couple back into fiber. But basically mainly because of this V effective being very large. So for fiber based Raman lasers, the threshold power is usually in the watt range. Okay, so you need to pump with quite a bit of power, but again recently once people figured out how to make these micro resonators, very small optical cavities on a chip, you can really lower this V effective to a very small value by orders of magnitude, okay, and also have this Q very large, okay, like 10 to the 6 or even higher. So people have brought this threshold power down to milliwatts. I think the record is like microwatt. So I posted a paper on that also, where they take a silica micro cavity, and basically it has very high Q factors, and they can see Raman lasing with only microwatts of pump power, okay, which is sort of, yeah, it was unheard of before. Okay, so this Raman kind of architecture can be used to make lasers where you can't make, again, traditional lasers, right? So, and this Raman shift can be quite large, right? So we saw, for example, in silicon, this Raman shift was about 15 terahertz, which means if you pump with a wavelength, let's say around 1.5 micron, then you can get lasing at Stokes, which is like around 1.8 micron. Okay, so for example, you get very good semiconductor lasers and amplifiers at 1.5 micron, but it's very difficult to make lasers at 1.8 micron. So what you can do is make a Raman laser lasing at 1.8 micron, pumping with. And also, what has been observed is that if you pump sufficiently hard enough, if you go to high pump powers, what happens is not only do you see the first Stokes, so okay, so let me plot in terms of wavelength. So let's say, this is my pump wavelength, right? So I go by Raman shift down in frequency, or in wavelength I increase the wavelength, right? So the shift is proportional to 1 over omega, I guess. So then you get lasing at Stokes, right? But then if you pump hard enough, the Stokes which is generated in the cavity also becomes strong enough to act as a pump on its own, and you can get secondary. So you can get like lambda S1 and then lambda S2. You can get like multiple Raman shifted wavelengths. Okay, so it's like cascaded Raman lasing, right? So for example, the next, if you go another Raman shift away, then the next Stokes will be at like 2.2 micron or something, right? So you can generate novel wavelengths lasers using this. So this has also been demonstrated, generating multiple orders of. So I've posted a couple of papers on Moodle regarding this to look at. Okay, so this is sort of what we've discussed is sort of the gain part, right, or the imaginary part of the susceptibility. But we also saw that there was a real part, right, which was sort of like a refractive index dependent on the pump power. right? And what that can be used for is sort of delaying optical pulses, okay, or what is maybe more popularly known as slow light. Right, so you know that, I mean, for optical communications or something, we are sending optical pulses, right, which are propagating through fibers or something. Let's say we want to synchronize different signals arriving at some place, okay. So we need to, let's say, delay signal in one arm with respect to the other so that they line up, okay. So in the electronic case, delays are sort of straightforward, right, or they're so-called buffers. But in the optical case, it's very difficult to do. Okay? But one way sort of people are exploring is like using this Raman scattering, right? So the refractive index now is dependent on my pump power, right? So by controlling my pump power, I can control the speed at which my Stokes pulses at the Stokes wavelength, for example, are going, right? So you can imagine that I can control the delay of the pulses which are at the Stokes wavelength using pump power. Okay, so that's sort of the idea. So recall that if you plot the susceptibility, Raman susceptibility, right? So at the Stokes, so the imaginary part looked like a Lorentzian, right? And then the real part looked like that. Right, and this at the peak is the Stokes resonant frequency, which is Raman shifted down from the pump, right? So omega SR is omega P minus the Raman shift. Right, so this is sort of the imaginary part, which gives you gain, right? So negative imaginary part we saw gives positive gain, and this is the real part. And if I multiply that by sort of the pump power or intensity, that gives me sort of the change in refractive index, right? So this we saw we could write as some quantity into R, like a nonlinear index coefficient due to Raman times the pump intensity gives me the change in the refractive index seen by the Stokes wave. So you can see that this refractive index change is now highly dependent on the Stokes frequency, right? It's not a constant. So imagine we are sending a pulse centered on the Stokes frequency, right? So the carrier frequency is the Stokes, but it is a pulse with some bandwidth, which means so let's say we have a pulse which is centered, the carrier frequency is the Stokes resonant frequency, and there is some bandwidth to the pulse. Okay, so then you can see that the frequencies in the pulse see different refractive indices, right? And so for the propagation of the pulse, we define what is called the group index, right? Which is, so this is sort of the phase index, right? And we can define a group index. Okay, so this variation in the refractive index, delta R, delta NR, So we can get this from the Raman susceptibility, right? So you can write it like this. Okay, where this delta is the normalized detuning, which is delta omega s by gamma, or omega s minus omega s resonance by gamma. Okay, so recall that the real part went as some delta omega s by delta omega s plus gamma square. Okay, so that's what we've written. And this GR is the peak, again the peak Raman gain here. Okay, so now of course this is frequency dependent, right? So you can define a group index. It goes like that. Okay, so the change in group index from so due to this change in the refractive index due to Raman, there is a change in the group index, which is basically the derivative of the change in this index with respect to frequency at the Stokes frequency. Right, so we can plot how Ng looks for this n. Right, it's basically the derivative of this waveform. Right, so if you take the derivative, you can see that it's positive. The derivative is positive in this range, right, and negative in this range. Which means if I plot Ng, so if I plot,
So can you explain the expression delta Ng?
yeah, so this you know, this standard, right? So now n is getting modified because of the Raman coefficient here. Okay, so then the change in the group index is basically the change, how much this changes, right? So basically I can write n as some n naught plus delta n Raman. Okay, so so the n naught plus omega d n naught by d omega will give me the group index of the material without Raman, right? And then there will be additional term which is d delta nr by d omega, which is the change in the group index due to Raman, right? Is that clear?
Okay, sir.
So the material has some dispersion properties on its own, right? And then we are modifying it due to the Raman interaction. And so we want to see how much it changes due to the Raman interaction. Right, so you see, so the group index will be positive between these two. So it will be positive here. And then it will go negative beyond this. So it will look like this. Okay, so your n, so we are. Okay, so this is how what Ng looks like. Right, so this is delta nr and this is delta Ng. So you can see that you can get a significant positive delta Ng here at the source. So if I have a pulse whose carrier frequency is omega SR, so and it has some bandwidth delta omega about that, so then it sees a group index which is modified by that much. So if the group index increases, that means the group velocity reduces, right? And that's why we refer to it as slow light. Okay. So this I can write in terms of the normalized detuning here like this. Right, and we just put this expression for delta nr here. So you'll see that delta Ng is okay. So delta is the detuning. So if we are centered on the Stokes resonance, then delta is 0. So delta Ng at delta equal to 0, or at omega s equal to omega SR. You can see this CGRP2 by 2 gamma A effective. Right, so basically, let's say you're propagating some length L, okay, then and you have some pulses propagating here, then due to the Raman interaction you slow the group velocity, so you basically cause the pulse to be delayed by some delta t. So instead of arriving now, it arrives delta t later, okay, and that delay, so the pulse delay that you get you can write as basically the length divided by the change in the group velocity, which is basically, so if I write the change in group velocity as or the change in L over Vg, so I can write it like this. Okay, so the pulse delay, how much I delay is proportional to this delta Ng times the length of the medium divided by 6. Right, and this delta Lg is now proportional to pump power. So by changing my pump power, I can change this delta Ng and change this delta T. So I can tune how much the pulse is delayed by controlling the pump power. See? So that's like a optical buffer or something, right? So you can control how much you want to delay the pulse by. Okay, and so again you see that the effect is larger for a larger Raman gain. So if you have a material with a strong Raman coefficient, then for the same pump power you can get a larger delay. And again, having a small mode area helps because that comes in the denominator, right? And this gamma is basically the line width, right? So 2 gamma is the line width here. So again, that is coming in the denominator, so a narrow line would help. So narrow line would mean that your group index now looks like that. So as the Raman line width narrows, the peak change in the group index grows. Okay. So again, you can see that crystalline materials would be much better because GR is higher, gamma is lower. But given that, again, a lot of the initial pioneering experiments were done with optical fibers, which is made out of silica amorphous material. Okay, so there was a lot of excitement initially that could make these all optical buffers and controllable delays with pump power, but sort of slowly there haven't been many applications for this yet. Yes. But nevertheless, it's an interesting effect that just by for controlling the pump power, you can delay pulses by controllable amounts. So similarly, at the anti-Stokes, it's negative, right? So the refractive index, so the real part of the susceptibility is the negative of the susceptibility at the Stoke. So the delta NR is negative, which means the delta NG is also negative. So instead of a positive change, you get a negative change. So at the anti-Stokes, you actually get an increase in the group velocity and your pulse advances. But at the anti-Stokes, it's not so interesting because you typically get lost automatically. Right? So it's not, your signal will get lost anyway, unless you have that cars.
So delta D is inversely proportional to gamma. So if the pulse is narrow, so it will delay. It will have less delay.
No, so delta NG was inversely proportional to
Gamma.
yeah, right. And so the delay was proportional to delta NG. So narrower line means more delay. So this is the line width of the Raman resonance, and of course your pulse bandwidth has to fit within the Raman resonance, right? So if you want to, so this is your NG, right? So of course your pulse bandwidth should fit within this to see this. So if your pulse bandwidth is really large, then it's not like most of your pulse is not seeing this NG, it's seeing some different NG, right? So then your pulse will first of all get distorted. And also, yeah, I mean, at that point, it won't be meaningful to call it a delay anymore because the pulse sort of gets distorted so much. Right, so bandwidth of the pulse has to be less than the Raman line for this to work. So a narrower Raman resonance leads to a larger delay, but that also means that your pulse bandwidth has to be narrower, which means you need longer pulses. Because smaller bandwidth means longer pulses. So what it's saying is for longer pulses you can get longer delay, and for shorter pulses you can get shorter delay. Right. So it's something like the delay divided by the pulse duration is sort of constant. So how many pulse widths of delay I can get is sort of invariant, you can't change that.
Sir, the point you explained right now, can you explain it again?
So
that one I understand, but the pulse should be.
Yeah, we also understood that the pulse band. So this is NG, delta NG, and this is gamma, right? So now if I want to delay a pulse, so the pulse has some duration in time, right, and it has some bandwidth in frequency. So let's say it's a transform limited pulse, which means this delta omega is like 1 over tau p, right? So this delta omega has to be less than gamma, right? So the bandwidth of the pulse has to fit within the Raman line. So then basically the whole pulse is seeing the same ng, right? So delta omega has to be less than 2 gamma, right? So if I take inverse, it basically means my pulse width has to be larger than this phonon lifetime, right? Which was the inverse of this gamma. So if I go shorter in pulse, if I have pulse widths which are shorter, then the bandwidth becomes more, right? And then now delta omega becomes greater than gamma, which means most part of the pulse is seeing now different NGs, right? So now, that looks like group velocity dispersion, right? You are seeing different group velocities. So then your pulse, instead of just getting delayed, will actually get distorted, right? It will spread and like what happens in group velocity dispersion.
I got
So
it.
to delay pulse without distorting it, you want the pulse width to be long enough such that the bandwidth is within the Raman line. Okay. Clear? So, yeah. Just one last thing I'll discuss before closing Raman scattering. So far we've sort of assumed the pump and Stokes, etc., to be again monochromatic waves, right? Pump at a particular frequency omega p, then Stokes shifted to a particular frequency omega s. Now you can also do Raman scattering with pulses, right? So right, so basically if you have a pulse moving in a medium which also has a Raman nonlinearity, then there could be Raman scattering occurring, which will again modify the spectrum of the pulse and also the time domain waveform, right? Just like the Kerr nonlinearity dispersion too. So recall that for pulse propagation in a nonlinear medium, we had this nonlinear envelope equation which described how the amplitude of the pulse or the envelope of the pulse changes with propagation. So we had a term for dispersion, right? So this dispersion operator here was right. So n equal to 2 is DVD, and then higher order dispersion terms if you want to include. And then we had the Kerr nonlinearity term. Right. So this first term is the self-phase modulation, mod A square A, and then we had this self-steepening term. Right. And for reasonable pulse width, unless you are very, very short, we saw that you can neglect this self-steepening term and just include n equal to 2 for the dispersion and get the NLSE and solve it. But in the most general case, let's say you have this, right? So now, if you have Raman nonlinearity, so this was due to the Kerr nonlinearity, right? So let's say if you have Raman nonlinearity in your medium also, then we modify the nonlinear term here. Okay. So remember, we started when we derived this, we started from an instantaneous response that we said, okay, the nonlinear polarization at time t was given by mod a square at time t times a of t, right? But in general, we saw that in the beginning of the course that we have to take a response function, right, of the medium. And we also briefly discussed in the last class that for this Raman nonlinearity, we can describe it in the time domain as with some response function, with this damped sinusoid kind of response function, right? So basically, one way to include Raman would be to modify this nonlinear term, okay? And instead of an instantaneous response, so include this statement. And now have a response function okay, so like a convolution of this response function with mod a square for the power. Right. So if you take this as a delta function, then we get back the original equation we had. Right. But now, so the curve nonlinearity we can assume like an instantaneous response, but the Raman nonlinearity we saw doesn't have an instantaneous response, right? It has this time scale of the phonon. So this R of tau, the response function, I can split into two parts. So one part is an instantaneous part for the Kerr nonlinearity. Okay, so this is the Kerr instantaneous part, and then another part, this fraction HR, which has the Raman response function. Right, so we discussed the Raman response function in the last class. So this R of so if FR is 0, then we get back the original equation with just the Kerr nonlinearity. But now, if the medium also has Raman, then we take the Raman with some fraction FR, right? So this FR is also now a material constant, which gives me the ratio of the Raman to the Kerr nonlinearity. Like what is the strength of each? Right. So, for example, again for silica in optical fibers, this FR is about 0.18. So the Raman contribution to the total nonlinearity is about 20%. For silicon, it's much smaller. It's only about 4%. If you take diamond, it's actually much larger. It's about 27 or 30%. Okay, so for different materials, you can see that how much the Raman contributes to the total nonlinearity, or how it compares to the Kerr nonlinearity varies with the material. Okay, so it's sort of a fractional strength of, so this FR is sort of like, you can think of as the ratio of the chi3 Raman to the electronic chi3, right? The Kerr chi3. Okay, and so to include this Raman response now, we can also simplify this equation a little bit more. Again, in the case where so if the pulse is not too short compared to the Raman oscillation time, right? So if tau p, the pulse width that the width of the pulse that we are considering propagating in this nonlinear medium, if that is longer than 1 over omega r, right? Where omega r is the Raman shift. Then, so this HR of t, if you remember, looked like this, right? This HR of tau was something like this, a damped sinusoid, where the time period was 1 over omega r. That was the resonance frequency, right? And this decay time of the exponential was 1 over gamma. That was the Coulomb lifetime. Right. So we are saying basically the pulse width is longer than this oscillation time period. Okay, which is usually the case for like greater than 100 femtosecond pulses, picosecond pulses, etc. So we basically do a Taylor expansion of this this term here. So we do okay. So we write the amplitude at t minus t prime or tau minus tau prime as the amplitude at tau minus tau prime times d over d tau times. Okay, so we sort of take the first, we do a Taylor expansion and keep only up to the first. Okay. So if we do this substitution in here, you can see that the equation will become, so this part so this had a delta t plus HR of t, right? So when this is the case, so then theta of tau prime a okay. So I put this Taylor expansion in here, right? So first term is a at tau, and the integration is over tau prime, so that I can just take a outside the integral. And then the second term, I have d over d tau of a tau, which also I can take out of the integral, and then tau prime will remain inside the integral. Okay. So typically this response function is normalized such that integral of HR from 0 to infinity is 1. Okay, so this is 1. And this is an integral of tau times the response function. So this is like an average response time, right? So I have this, like you can think of it like a probability distribution. So the integral is 1, and then I'm multiplying by the quantity times the probability. So that's like average, right? So I can define that as some TR, which is
Sir,
the Raman.
so the bottom
Yeah.
part is not visible, sir. On the left hand side at the top.
Okay, I said there. So this, so this first term is clear. This is clear,
Yes, sir. That one is clear.
right? So the second term, this is minus d over d tau, right? So that's this, which is not dependent on tau prime, so that comes out of the integral. And then inside the integral, I have this tau prime times HR, which comes. Okay, right? So this is like an average response time, right? So this is like a response function, or like, as I said, you can think of it as like a probability distribution function, right? So the integral is 1, and then I multiply by that quantity times that function. So this will give me some time scale, which is like the average response time, right? That clear? So like the expectation value of some x is integral x times the probability density function, right? Basically the same, where this probability density function is normalized like to 1. Right? So this is some average response time, which we call TR. So some Raman response time TR. Right? So this you can calculate because you know what HR tau is for a given material. Right? So you can calculate what this would be. Right? So this would be related to this like phonon lifetime, etc. So, well, the bottom line is basically for a given material, this TR is a constant for a given material. So, um, so TR is defined as FR times this, because remember this R of T had, right, so this R of T was FR HR of tau plus 1 minus FR delta of tau. So this FR comes with HR, so HR times this integral is defined as tau R or TR. Okay, so then this equation just reduces to, so this delta part will give me the same the Kerr nonlinear term, right? But with now a factor 1 minus FR. Right, and then from the HR part, I will get this term, which is also now like the Kerr term only, because mod A square, this you'll get a mod A square times A, but now that comes with FR, right? So FR multiplied by this whole thing. So you'll get 1 minus FR plus FR for the mod A square A, which will just give you mod A square A. Okay, and then the extra term which will come will be this second part, which will be TR times this D or D tau times mod. Okay, so the equation will become Okay, so the equation will become this. So you can see up till here we already had with the Kerr nonlinearity, and then due to the Raman we have this etc. Okay, so this is due to the Kerr, and this is due to. Okay, so for example, again for silica, this PR is about 3 femtosecond. Okay, so for different materials, this Raman response time, or sometimes known as the Raman shock time, is a material dependent quantity. So in the ultra short pulse propagation, if you want to include Raman also, then you basically include this term in addition to the dispersion and the Kerr nonlinearity term. Sorry, I think this comes outside. Okay, and so now, of course, this is a complicated equation. Again, you need like numerical techniques to solve it. So typically, yeah, people solve it on a computer. But what people have used this kind of thing for is, so now you have a lot of different nonlinear phenomena all happening together in a medium, right? And what it can lead to is like extreme broadening, and you can get what is known as supercontinuum generation. Okay, so if you send in a very high power pulse in a medium which has Kerr and Raman nonlinearities, then you know that Kerr, due to self-phase modulation, etc., can lead to broadening of the spectrum. Then Raman can lead to shift scattering to lower frequencies toward the Stokes, right, which get amplified. And these two things happen together, and the spectrum keeps broadening and broadening. Okay, and what you can get is very extreme broadening. So let's say my input pulse, so this is omega, is very narrow band, right? So the input pulse is almost as a single frequency, but with a very small bandwidth, let's say a terahertz or something like that. But then due to this multiple nonlinear phenomena happening in the medium, you can get extreme broadening in your spectrum, and you can go from something like omega naught to 2 omega naught. Okay, so what is known as octave spanning, right? So for example, in the visible spectrum, you could go from 400 to 800 nanometer, cover the entire visible spectrum, right? And even broader, people have even shown like multiple octave spanning. So if you design your medium well with the right dispersion and with these nonlinearities coupled together, if you send in a very intense pulse, basically you get this extreme broadening, and this thing is called supercontinuum because basically it's a continuum of frequencies over a very broad range. So it's like a white light source, right? It's like a broad spectrum, but it's coherent because all these frequencies are being generated through nonlinear interactions, which are coherent, which is different from a light bulb, right? Where basically you just have thermal radiation. So it's not coherent. But these kinds of light sources are broadband and coherent. So that's something that is very useful and used in many places. Okay, so so that's a very important application for sort of this ultra short intense pulse propagation in nonlinear media with Kerr and Raman nonlinearities. there's a chapter on this in Agarwal if you want to explore it further at some point. Okay, but I just wanted to mention because it's an important application, especially nowadays. Okay, but what kind of spectrum you will get is very complicated, right? Because this propagation equation is very complex. This dispersion can have many terms because once you have a broad spectrum, then higher order dispersion terms will start contributing, right? You need to take this self-steepering term now also, and of course you have the Raman term. All of them coupled together. Okay, so but yeah. So these kind of sources have now been made across different parts of the spectrum, like visible, infrared, mid-infrared, all the way up to like 10 microns, starting from maybe 300-400 nanometers up to 10 microns over their entire wavelength range. People have made these kind of sources.
So then you said that coherence remains in the pulse. So because the pulse these frequencies are generated due to non-linearity. So if we have to show this, we have to move to the quantum domain, or we can classically show that.
No, it's all classical, right? So what do I mean by coherence? If you do interference, you will see fringes.
Yes.
Right. So for example, you take this broad spectrum light source, do interference, and you'll see fringes at different parts of the spectrum. Okay. So typically, like if you take a source from a light bulb or some halogen lamp or something, if you do interference, you won't see any fringes, right? Because it's a thermal source and there's no well-defined phases to the fields.
No, if we have to show it mathematically, sir, then.
So mathematically, you evolve the field, right? So you know what exactly the electric field is as a function of time, right? And so what is interferometry? You take the amplitude electric field, and then you delay it by some value, right? And then beat the two fields, and then calculate what you detect, and then vary this delta t, right? So and if you vary the delay, you'll see bright and dark, high and low.
Okay, sir.
You can mathematically do it. Of course, analytically, it's not possible to show, as I said, because it's a very complicated equation. But numerically, you do this. You solve for the fields, you plot what the interference looks like, and you can actually calculate what coherence you will get.
Okay, sir.
So, of course, the amount of coherence might be different in the different parts of the spectrum. Like some parts of the spectrum might be more coherent. The visibility of the fringes is large. Some other parts might have lower. But overall, the spectrum is sort of it's coherent. Whereas if you do it for a light bulb or some thermal source, then as you vary delta t, you don't see anything. Right? You don't see any fringes. So this is useful, for example, in medical imaging. They do what's called as optical coherence tomography, okay, where basically they're doing interferometry with these very broad light sources, and then depending on what kind of sample you go through, these fringes change. It can be used to sort of image samples which are difficult to image otherwise. It's also useful in other kinds of things like optical clocks and spectroscopy. Yeah, so as I said, if you want more details, there's a whole chapter on this in Agarwal.